All right, now on to velocity. With velocity, how are we going to do this? Well, to make velocity, we have to start with the current position of a point and subtract that from a position of another point. So if we have the position over here, to make this vector, to make that line, we need to subtract these two positions. So what position are we going to use to dictate the direction of these velocity vectors? We could use the normal, but the problem with the normal is that it just creates one giant fuzzy puff, and it doesn't really have a lot of detail that is going to make this look great. So instead, what I like to do is I like shrink wrapping this whole thing. And I know that green's kind of difficult to see, so I apologize. But we shrink wrap this whole thing and we scatter points along the outside. That way I don't have any points happening, let's say in here and along here. I want everything generally pointing outwards away from this general plume. So that's why I'm not doing the normals. I don't want it actually blasting into this shape. And besides, that's kind of what pressure does anyways. And we want something that's a bit more directional than pressure when doing this initial velocity. So with that being the case, once we have our shrink-wrapped objects, we have our points scattered along that object, we'll take the difference, give ourselves some velocity vectors, and once we have these velocity vectors, we'll then use that within a particle simulation, add a bit of extra turbulence to that motion, and that will give us a nice bit of detail without things getting too chaotic. So without further ado, let's start here at our geometry level. Before everything gets turned into a volume, we're going to use the shrink wrap like this. And that will give us this shape right here. Now, if we go out from here, there's going to be a problem in that some of these areas are actually going to be facing inwards. It's kind of difficult to see, but you can see that crack right there. And so if we scatter some points with this, it's not going to be exactly what we're after. It'll give us weird artifacts. So what I like doing is setting this to 0 to start, so we don't have those cracks in the surface. And then we'll turn this into a volume. So VDB from polygons. That's an SDF volume, maybe 0.05. We can then use a SDF reshape to dilate this out, maybe about 1.5. So that expands that boundary just a little bit. From here, we can convert VDB back into polygons, and then we could set the normal and scatter some points. And let's actually give ourselves some room here as well so that this doesn't get too out of hand. Okay, so we have these points. Let's turn off the relaxed iterations and bring this up to, for right now, around 20,000 so that we can see it. All right, so once we have this, we need to subtract the position of these points with the position of points scattered within this fog volume. So we're going to scatter some points in here, like that. Force total count, let's say 300,000. We want a fair bit of points within here. It's going to take a while to think about that because of the relaxed iterations down here. So that's why I always turn that off. You can see down here it says relaxing points. So turn that off, it'll be a lot faster. And now that we have these two sets of points, we can use a point wrangle to determine that initial velocity. So taking this guy, we want to make velocity on these points, and we want to take data from over here. So start off by saying we want to take the original position minus the sampled vel from over here. So velocity is equal to that. Now, what's going to be sampled vel? That's going to be a vector called sampled vel, and that's going to be equal to the point function. The point function needs to read off position, so we'll say index number 1, that's input number 2, going through here. Look for P for position, and how should it know which point it needs to read? Well, it can find the nearby points. And how are we going to get that nearby points? Well, there's a function called near points right here, which finds the nearest points. So go through again, input number 1. We're going to use, I believe, our position, and we'll store this as an integer variable like that. So as soon as I do that, let's turn on our vectors. We could see that, yes, in fact, we do have vectors, but they are heading in the opposite direction. So let's take our sampled vel minus p and switch that out. There we go. Now, you'll notice that as we get closer towards the center, these vectors become more and more intense. And I don't want to start off with that. So we also have a function here called the normalize, which will basically make all of these vector lengths the same, equal to about 1. So that just normalized all of the lengths right there. And that will get us started with what we need. So let's call this point wrangle our set velocity right there. And again, I'm going to take these guys down so that we have a little bit of extra room. And now I'd like to emphasize some of the areas along the edges of the shape so that the, let's say, areas up top here can have a greater velocity. Now I'm thinking about what direction I want things to generally go in. And right now, if we take a look at the shape of this, I would imagine that we want a bit of extra velocity going in this direction as well as going up, maybe a few areas over here and back here. But if you want to be specific about that direction and give the velocity a bit more of a push, then there's another way of doing that using the paint attributes, or the attribute paint sop right here. So what I'll do is I'll say, okay, I want extra juice up here at the top. So I'll start painting that out. And anywhere where I want this explosion to be more intense, I'll go ahead and paint that out like so. This also, by the way, is going to be dictating the shape of an invisible collision object that I'll teach you how to do here later on as well. But let's say that we have these areas. We like velocity happening a little bit more intensely around here. We can then take a smooth, and we can smooth out that mask attribute. So instead of P, we'll say mask right there. And right-click on this, check on mask so that we can see it. We can go ahead and take down this filter quality to give us a bit more blur like this. And also what we can do is say that there are no constrained boundaries so that this goes through disconnected pieces like that. So as soon as I do that, we end up with this, and we can take this attribute as a multiplier to our velocity. So if we go down to our set vel, let's take our third input over here and bring in some data from that mask attribute. Within this wrangle, we now need to read in data from that third input. And so we'll need to have a nearby point being recognized, as well as reading off that mask attribute. So this whole thing can basically be copied with a different naming structure in mind. So nearby points, vel mask, is going to be this. Set the input to index number 2. Point function is also going to be index number 2. And sampled vel mask is going to be what that gathered data is. So that's all going to be multiplied against velocity. So sampled vel mask. And I also want to read off an attribute called mask right here for those values. So again, just to restate what I did there, we read the nearest points so that we can then sample the attribute values over here. That's the mask that we just painted out. And we're taking those values and multiplying that against whatever we came up with here with the initial velocity direction. And one last thing, we need to sample the nearby point velocity mask points. So in other words, the points that belong to the geo where we painted that mask over here. I forgot to put that in our point function earlier. as soon as we do that, we should see vectors that are stronger up here. And these guys go to 0. Why? Well, if we look back here, all these purple regions are a value of 0. So we need to change the range of values that we see right here. Easy to do. Just create a point wrangle, and all we'll say is mask is equal to the fit function. What are we fitting? Well, we're fitting those mask values. The old min used to be 0, the old max used to be 1, and now I want the minimum to be 1 and the maximum to be 10. So these red areas are going to be 10 times the velocity of what it normally was. Okay, this looks kind of crazy, but if we go to our mask visualization, we say the maximum is 10. There we go. The blue area is 1. This is 10. Right on. Well, this all goes down to the set vel, and as you can see, now we have those areas working properly. All right, from here, let's do a file cache. We'll call this our particles velocity source. We only need one frame here, so get rid of $F4, save that to disk. Once we read that in, create a popnet. In here, we'll change the source to say points, birth 250,000. I found that worked pretty well for what we need. Or, you know what, let's just do all 300,000. 1 second, we'll hit all 300,000 points. Okay, as soon as we do that, go to our attributes. We are inheriting that velocity. I'd like to set that to 0.5. I already know that I'll need a pop drag, and we'll set this to 0.1. And if I go forward, we end up with this, which is cool. We have all those directional areas happening, and things are heading away from the plume, which is exactly what I want. Now, to add more detail, let's also use a pop force, a couple of them actually, and I'll set the amplitude to 2, swirl size to 5. Let's make another one. This guy is going to be a swirl size of 2. And now we should have this, which, if I just kind of scrub through, gives us something around there. Let's also change the birth so that our life expectancy is about 0.75 and life variance is 0.25. We want these guys to die off relatively quickly. And what I'm looking for here is to have those directional areas still happening with just a little bit of extra detail with that pop force. And that's what we have right here, which is great. All right, as soon as we have this, we'll want to delete any points that are happening down here. We don't want to waste voxel data on trying to turn this into velocity. So, group, we'll call this our blast points. We'll keep in bounding regions using a bounding object. That's going to be our object merge. And we will look for our terrain. So combine geo islands, Calis polys out. And now we've grouped those points. Last but not least, blast them out. And we want the blast points right here. Points, and we're good to go. Okay, cool. From here, let's create a volume rasterize attributes. We are trying to rasterize V. Let's go down here, get rid of that coverage attribute density, and normalize by clamped coverage. The particle scale, let's set this to about 0.2. Volume slice, so that we can see this. And let's take our minimum filter size up just until this blurs out a tad bit. So right there. Perfect. Also, let's do velocity blur, shutter offset 0.5, shutter 2. That just kind of blurs this out a tad bit more. And that should about do it for the volume rasterized attribute. If we middle mouse, we have about 260,000 voxels. We could take this voxel size down a tad bit if you want, so maybe 0.075. And yeah, that's not too bad. For the vector 3 voxels being at 510, that's not too bad. And once we have our velocity, bring that in with temperature and fuel right here with this merge. That all comes together, and in the next video, I'm going to organize everything we have. It's getting a little bit crazy, and I think at this point we need to start sectioning things off just to keep track of where we're at in the network. So I'll organize that, and also in the next video we'll work on density.